let's talk a little bit about what I find to be one of the more mysterious forces of the universe. Actually, I find all of the forces of the universe to be fairly mysterious. So let's talk a little bit about charge. And we've all heard of charge. Charge the battery. This particle has charge. But when you really think about it, all charge means is that there's this property called charge. And we know that if something contains a positive charge, and calling it positive is a little bit arbitrary. It's not like protons have a little plus written on them. We could have called them negative. But that when something has a positive charge and when something else has a positive charge, that they repel each other. And we also know that if I had something else, another particle that happened to have a negative charge, and once again the word negative being applied to this is completely arbitrary. They could have called it blue charge and red charge. But all we know is that when another object has the other charge, in this case we call it negative, that's going to be attracted to a positive charge. Right? So what do we know about charge? Charge is a property that particles have, and if you put enough particles together, I guess objects have that property as well. So it's just a property. And that's a way of saying that I really don't know what it is. And frankly, no one fundamentally knows what it is. Actually, no one really fundamentally knows anything. But charge is a property of particles and objects, just like mass. I mean, if you think about it, mass is just a property, and to some degree it seems a little bit more real than charge, because in our brains are wired to in some way comprehend what mass is. But we're probably more comprehending weight and volume more than mass, but we can think more about that at another time. Charge is a little bit more abstract, because before we started rubbing amber into our hair, we really didn't experience much charge unless we got struck by lightning. So charge is a property that particles or objects have, and we know that there are two types of charge, which we've arbitrarily named positive and negative. And we know that like charges repel, and opposite charge attracts, or unlike charges attract. Right? So what can we do with this? Well, if we have this property, I think a useful thing to do would be to measure the property, and so we came up with units. And so the unit of charge is called the Coulomb. It's named after a scientist in the late 1700s who played around a lot with charge. You can look up more about him on Wikipedia. But it's called the Coulomb. And the Coulomb, there's a bunch of definitions, but I like to think of it in terms of elementary particles, just because to some degree, well, unless you start going into quantum theory and start talking about quarks and stuff, the elementary charge is the charge on a proton or a neutron. So I'll go into more detail in the future on actually the structure of atoms and whatever else. But let me just draw a little example. So a atom tends to have some neutrons in them, which don't have this charge property. It'll have some protons in them, which have a positive charge. And once again, that's kind of arbitrarily defined as positive. We could have called it has a red charge. And then it has these things floating around that are much lighter than the much lighter than the protons and the neutrons in the nucleus. And these are called electrons. It's not even clear that they're real objects. They're almost like energy. But sometimes it's useful to view them as objects. Sometimes it's useful to view them as well, not as objects. And we'll go into all of that more later. But electrons have a negative charge. And the fundamental unit of charge, as far as we are concerned right now, before we start talking about quarks and other potentially subatomic particles, is the charge in an electron or a proton. And they have the exact same charge, and that elementary charge is denoted by E. And to be frank, I'm not sure whether E stands for elementary or E stands for electron. But actually, E is equal to the charge of a proton, so it probably stands for elementary. Charge of a proton. And the charge of an electron is the negative of this. So negative E is the charge of an electron. Charge of electron. But if we didn't care about sign, then the magnitudes are the same. So that's the fundamental as far as we know, or so far in our physics. That's the fundamental charge. The fundamental unit of charge is just the charge in a proton or a neutron. So how does a Coulomb relate to that? Well, a Coulomb, which we'll denote by C, is equal to, and this is a bit of an arbitrary number, but when we start doing things with electricity, we'll see why the Coulomb was defined the way it is. But a Coulomb is 6.24 times 10 to the 18th e's. Or you could say it's 6.24 times 10 to the 18th times the charge on an electron. Actually, times the charge on a proton. And then, of course, in terms of magnitude, because if I just say Coulomb, I'm not really giving a direction. So if you look at the other way around, you could say that the elementary charge is equal to, at least its magnitude, 1.6 times 10 to the minus 19 coulombs. So fair enough. This might be a useful number to memorize, but it will usually be provided for you in some way. So what can we do? We say that these objects have this property called charge. Like charges repel, unlike charges attract. If we have enough of these protons if together, then the whole object has charge. If we have more, let's say, protons than electrons, then we have a positive charge. If we have more electrons than protons, we have a negative charge. And we know that we've defined this unit of charge called the Coulomb, which is a bunch of the fundamental charge. So let's play around with this and see if we can measure charge. So in part of the initial, I guess we could call it definition on what charge is, I said that that like charges repel, right? Like charges repel. So if both of these are positive, they're going to repel each other. And unlike charges, if this is negative, this is positive, they're going to attract each other, right? So by definition, if they are moving each other, these two particles are going to accelerate away from each other. These two particles are going to accelerate towards each other. The charge between these particles, or the charge in each of these particles, must be generating some type of force, right? If there was no force being generated, then they wouldn't repel or attract each other. And this is where we get to Coulomb's law. And this is why we name charges after Coulomb. Coulomb figured out that the force between two charges is equal to, and this is going to be a vector quantity, and in about 30 seconds I'll tell you which, what happens with the direction, is equal to some constant times the first charge times the second charge divided by the distance between them squared. And this is pretty neat because this looks an awful lot like, so if we call this the force, the electric force, that looks a lot like the gravitational force equation. Let me write that down. The force from gravity between two masses is equal to the gravitational constant times m1 times m2 divided by the distance between them squared. So far, the two forces that we've covered, gravity, and now we're covering electric force, and we'll eventually expand this to electromagnetic force. It seems like they kind of act at distance in a similar way, and both of these forces apply in a gravity, in a vacuum. So it doesn't matter if you have no air, if you have no substances between the two particles. Somehow they are communicating with each other, which I find kind of amazing, right? You can have nothing between these two particles, but somehow this particle knows that that particle's there. And that particle knows that that particle's there, and they start moving without having any, it's not like they have a wire connecting to each other and someone's telling the other particle, hey, there's a particle there, start moving. So I don't know if you find that as amazing as I do, but think about it and you might. And it's just like gravity. I mean, the two masses, they're in no way connected. They could be sitting in a vacuum, but somehow they know that the other particle is there. And when we start learning about special relativity and all of that, we'll learn that, maybe there's nothing there, but maybe the masses are actually somehow shaping the universe. And maybe that's happening with the electric charges as well. But all we know at this point is that we have these charges and that they exert a force on each other that's proportional to the product of their respective charges divided by the square of the distance between them. And this constant right here, that is, I always forget it. What was it? I think it's 6 point. I always forget what that constant is. It is 9 times 10 to the 9th. So it's rounded, of course. That would be amazing if it was exactly 9. 9 times 10 to the 9th. And the units are Newton meter squared per Coulomb squared. And why are those the units? Well, pretty much because at the end we have Coulomb, Coulomb, so we're going to have Coulomb squared divided by meter squared, and we want to finish with newtons, so we want to cancel out the Coulomb squared by putting it in the denominator. We want to cancel out the meter squared by putting it in the numerator, and then we'll end up with the newtons to get the force. So that's just where the units come from. So given that, let's figure out the force between two particles. So let's say I have, and I've spent 10 minutes with a pretty long-winded explanation, but the actual problems you'll see in your physics class are pretty straightforward when it comes to Coulomb's law. So they'll say, hey, we have a particle here that has a positive charge of, let's call it, I don't know, plus, let me think of a good number. I don't know, plus 5 times 10 to the minus 3 coulombs. So that's a positive charge. And then we have a negative charge here. And let's say that, I don't know, how far will I make them? Let's say that they're half a meter apart, 0.5 meters apart. And then I have a negative charge here that is, let's say that this is 10 minus 10 times 10 to the, I don't know, minus 2 coulombs. So what is the force between these two particles? So if we just plug them into Coulomb's law, we get the force due to electricity, due to the electrical force, not due to electricity. We haven't done that yet. The static electric force between those two particles is equal to the constant, 9 times 10 to the 9th, 9 times 10 to the 9th, times the first charge, times 5 times 10 to the minus 3, times the second charge, let me do that in a different color, times minus 10 times 10 to the minus 2. I just rewrote that, although you probably can't see it. Divided by the distance squared, so 0.5 squared. We just plugged into this formula. So that equals, let me see, so 9 times 0.5 times 10. I'm just going to do the 10 separately. So that's times minus 10. So it's minus, this is 0.5 times minus 10 is minus 5 times 9 is minus 45. And then 10 to the 9th, minus 3, so 10 to the 6th, and then minus 2, so 10 to the 4th, times 10 to the 4th, divided by, and what's 0.5 squared is 0.25. Right? And this is equal to what? That's equal to 4 times this top 160, plus this is equal to minus 180 times 10 to the 4th newtons. And actually, this might seem like a large number, but these charges that I put here are actually fairly large charges, and hopefully you'll get a sense for what's a big or a small charge later. But these are reasonably large charges, and so that's why there's a relatively large force exerting between these two particles. Now, we got a negative number, so what does that mean? Well, we know that unlike particles attract, right? Almost by definition. And in this case, we had a positive and a negative. So when we have a negative, when we end up with a negative force, when we use Coulomb's law, that means that the force will draw the two particles to each other along the shortest distance between them. I mean, it's not going to make them go in a curve. It kind of makes sense. If we had a positive there, that means that the force was repelling the two particles. And if you ever get confused, just think about it. If they're both negative, they're going to repel. If they're both positive, they're going to attract. I will see you in the next video.